All right, let's go ahead and get started. My name is Praveen Rokhaya. I'm the science coordinator of the Global Water Futures Core Modeling and Forecasting team. Today, I'm pleased to welcome Dr. Hamid Morakhani, who is presenting a webinar on towards a holistic depiction of vulnerabilities and risks in extreme events, the notion of compound flooding. Dr. Morakhani is the Alton and Scott Endowed Chair of Hydrology in the Department of Civil Construction and Environmental Engineering, and also the founding director of the Center for Complex Hydrosystem Research at the University of Alabama. Previously, he was a professor of Civil and Environmental Engineering and director of Remote Sensing and Water Resources Lab at Portland State University. Dr. Morakhani is a pioneer in developing state-of-art basin data assimilation and uncertainty quantification methods that are widely used in different disciplines and variety of applications. His research emphasis is on harnessing data revolution, predictive science, machine learning, data analytics, remote sensing, and high-performance computing in the context of all system science. His research also advances our understanding of hydrological science through modeling climate-water-human interactions and food energy water nexus. He is the editor of the AGU Earth's Future and serves on the editorial board of several journals. Dr. Morakhani is also a fellow of American Society of Civil Engineers, a fellow of Environmental and Water Research Institute, and recipient of several awards, including ASC Edith Land's Hydraulic Engineering Award, Outstanding Research and Innovation Award from the American Association of Water Research Engineers, a Faculty Research Excellence Award, and Branford P. Miller Award, to name few. Without taking much time, I want to kick off this webinar by thanking Dr. Morakhani for accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Morakhani, the floor is yours.
Thank you so much, Praveen, and thank you for the opportunity to share some of our research over the past few years. And I'm going to present some of the recent works. And thanks to Martin Clark for earlier invitation to this seminar series at GWF. I'm very excited to present a lot of works we have. I hope I can fit it within the 45 minutes. So without further ado, because the notion of this presentation is about flood modeling and flash flood. Obviously, flash flood is among the most catastrophic natural hazards, which causes disruption in the environment and societies. And as you know, flooding is a socioeconomic risk that is likely to increase in the future under climate change and human development. And this risk has led to a variety of studies on the natural and anthropogenic causes of floods. So therefore, massive socioeconomic impacts caused by extreme floods provides a clear motivation for improved understanding of flood drivers. Here I'm showing 2 decades of flash flood events visualized for each month of the county scale. And as you see, we have about over 74,000, nearly 75,000 flash flood events analyzed over the past 2 decades, and 40% of those events cause property damage, with mean duration of these floods 4 hours and nearly 1,400 fatalities and over 6,000 injuries and 4,000, about 290 per year. And here I'm showing the frequency of a few variables associated with floods and some of the lessons learned. First is we see that the state of Texas, for example, indicates the highest values in terms of number of events, injuries and fatalities. And also 2 hotspots of flash flooding in terms of injuries and fatalities are seen, and these are Arizona and Central Texas, as we see from the figures. And generally, East Coast is more hazardous in terms of flash flooding than West Coast. We see a slight increase of number of flash floods over the years, but substantial increase in property damages. And Hurricane Harvey itself caused the highest property damage and abundant mortality. And as shown in the green box on the figure on the right, the 2012 was the year with least number of flash floods and lowest property damage, which is obviously the year we experienced a significant drought in US. And here I'm showing the median of flash flood duration with probability of 50%, which is about 2 hours. And east, north, central states shown as ENC region shows the highest flash flood duration among other regions, sometimes up to 48 hours in extreme cases. And frequency of flash floods, according to National Weather Service, flash floods generally initiate within a few minutes up to less than 6 hours of an intense rainfall. So the rapid onset of flash floods limits an effective and timely decision-making and cause the highest number of casualties on average as compared with other types of flooding. So the table that you see on upper right here provides a summary of the study area presenting the number of counties and flash floods in each state and also their property damages during 1996 to 2017 when we conducted this study. And these are all based on NOAA storm events database. And the total number of flash flood events, the number of events that cause property damage and the ratio of these two during this period are all shown in the figures that you see at the bottom. And the counties with highest vulnerability to flash flooding will generally result in more damage. So in that sense, Mississippi, South Carolina, and Louisiana are identified to be susceptible to flash flooding, whereas most of the counties in North Carolina indicated a low damaging ratio. Now the question is how we can enhance the predictability to protect the livelihood and property damages. And I should acknowledge or give the credit to Martin for this figure that he presented a few years back, and I borrowed that figure here to explain the hydrological and meteorological predictability. So understanding and enhancing the predictability of flooding generally must consider two approaches. First is the atmospheric perspective that we just call it meteorological predictability. That emphasizes synoptic scale, atmospheric circulation patterns, and the predictability of precipitation inputs in general. For example, a slowly propagating frontal system and intense weakly forced localized thunderstorms are generally known to be conducive to precipitation extremes across the Southeast United States, and the specific structure of circulation patterns associated with such extremes may vary by basin. And my mouse was about to fall, actually. I think, yes. All right. So the second perspective is the watershed perspective that focuses on the state of catchment, including land cover, slope, aspect, morphology, and initial condition, and the nature of the precipitation inputs to drive an understanding of the causal mechanisms related to flooding. So my focus today is mostly on the second one, but I'm going to touch on the meteorological predictability right after this. So based on the studies at the watershed scale, the proximate natural causes of hydrologic floods can be classified as single-day rainfall that rapidly exceeds infiltration capacity, multi-day to week-long rainfall that exceeds soil moisture holding capacity, and several-day rainfall that results in a combination of the mechanisms associated with single and multi-day rainfall, and also the snow melt and rain on the snow, of course. So while the natural causes of annual floods have been well studied and summarized for each state in the United States, surprisingly, the assessment of natural causes of extreme floods is often limited to event and regional scale analysis. So given the extensive damages caused by extreme floods, it's imperative to develop a unified understanding of the natural causes of extreme floods at a near continental scale. In particular, focusing on atmospheric circulation patterns leading to heavy rainfall can be especially useful to inform continental scale modeling and forecasting efforts. And let's touch on the look at some results. And in our work, we used self-organizing math, a type of artificial neural network, to perform unsupervised clustering of climate reanalysis data across the continental US. And we did this to just identify synoptic scale atmospheric circulation patterns associated with extreme floods. Then we assessed the flood characteristics like frequency, spatial domain, event size, and seasonality, all is specific to each circulation pattern. So on the left, you see the natural frequency, the annual frequency of the flood occurrence. We express it as percent of gauges associated with that pattern relative to all reporting gauges in the United States at time of flood. And on the right, you see the most prominent pattern for each grid cell, where the white area in this figure indicates no gauges in that grid cell, and a dot indicates at least 50% of peak over threshold floods were caused by the pattern. So we assess the physical interpretability based on three factors that are beyond the patience of this presentation, but I encourage those of you interested in that, please see our publication in Nature Scientific Reports as I'm listing it here. And let's touch on the vulnerability a little bit. Although numerous studies have estimated different aspects of vulnerability to more visually damaging hazards in the United States, like tornadoes, hurricanes, and floods, and there is not yet any comprehensive assessment of flood vulnerability across the continental US. So vulnerability is a result of combination of different parameters, which is the function of its exposure, sensitivity, and adaptive capacity. So exact definition and calculation of vulnerability may vary depending on the field of research. Generally, methods can be grouped into biophysical approaches and also socioeconomic approaches, or it could be an integrated approach. In our work, we employed an integrated assessment approach, combining the attributes from the biophysical and also socioeconomic approaches, and conceptualized vulnerability as a function of exposure, sensitivity, and adaptive capacity. Just to give you a little definition of each of these three components, by exposure, we mean the frequency of flood, for example, or the state population, etc. And by sensitivity, we mean the state's likelihood of being negatively impacted by flood, taking into account industries like agriculture, water, recreation, and hydropower. And by adaptive capacity, we mean a state's preparedness for flood and ability to recover, by looking at the state's flood plan and irrigation infrastructure, for example, and economic strength. Generally, building resilience to flash floods requires understanding of the socioeconomic characteristics of the societies and vulnerability to extreme events, and also a compound effect of the sensitivity of a population and its capability to respond to and recover from the consequences of a natural hazard generally construct the socioeconomic vulnerability. So in our study, we identified the categories that we developed the basis of socioeconomic vulnerability. We call it SEVI, S-E-V-I. And these categories include, as you see in the table, demographic socioeconomic status, race and ethnicity, age and gender, employment, housing and transportation, and industrial economy. So we use them all, and so there is a lot of data to be used. And due to the high number of variables describing the social vulnerability, generally statistical procedures are used to reduce the data dimension. One of the most famous procedures is the principal component analysis, which has been widely utilized for decreasing the data dimension. However, we found that one shortcoming of using PCA-based index is that this procedure falls short in dealing with missing values, and we have a lot of missing values in our data set. Therefore, we decided to employ probabilistic principal component analysis, or PPCA, for building the socioeconomic vulnerability index. And here is the calculated SEVI, or socioeconomic vulnerability index, of each county, classified into 3 classes of high vulnerable, medium vulnerable, and low vulnerable. So the low and high vulnerable counties are the ones placed in the 10th and 90th percentile of the calculated index. And as I'm showing in this figure, and the most vulnerable counties are concentrated in the Southwest and the Southern Plains, that is Texas and Louisiana, as well as the US-Mexico border regions of Texas. And the least vulnerable counties are located in New England and the upper Great Lakes. And in our study, we targeted 4 characteristics of flash flood, including frequency, magnitude, duration, and severity. And I summarized the result from the hotspot analysis in the figures that you see here on the right. And hotspots generally represent the spatial clustering of high values for a given characteristic. And the spatial clustering of low values are shown by the cold spots. And here on the left, you see flash flood fatality per million capita, where we divided the states in low vulnerable, medium vulnerable, and high vulnerable counties. And the figure on the right represents the flash flood hazard characteristics at the county level, as I mentioned before. So the red counties are the ones with where the stations show hotspot, and for that, the specific flash flood characteristic, and the green color indicates the coldest spot. So the counties that are located in the Pacific Northwest indicate hotspot for the flash flood magnitude and severity, but that's not the case for the duration and frequency. And finally, we use a 2-way cross-tabulation to map the coincidence of SEVI and flash flood hazard characteristics, and comparing the results with respect to flash flood duration and frequency. The high vulnerable hotspot counties for frequency are located in the lower southeast, basically. And whereas the high vulnerable hotspot counties for duration are located in the Southwest and Pacific Northwest. And the majority of high vulnerable cold spot counties, like regions associated with high vulnerability and low hazard, are concentrated in the Southwest for flash flood duration, frequency, and magnitude. However, they are scattered in regard to severity. So overall, and take-home message is that the majority of areas located in the hotspots of rapid floods exhibit low socioeconomic vulnerability index. However, hotspots and high socioeconomic vulnerability do intersect and affect a considerable number of counties in the United States. So for more information, you can see our paper published in Nature Scientific Report in 2020. And now that I discussed the causative mechanisms associated with flood and the vulnerability assessment, let me shift the attention to tropical cyclone and how we can communicate their hazard effectively that inform hurricane-induced flooding as well. As you know, the tropical cyclones are among the most devastating natural disasters that pose risk to people and assets all around the globe. Here, I'm showing the track of 17 costliest TCs and their corresponding precipitation magnitude based on HERDAT2 data and also rainfall from NLS2. The interior and exterior pie chart that you see on lower right illustrate the categories based on the Saffir-Simpson scale and the relative rate of damage caused by each tropical cyclone. And the color from yellow to dark red are to specify the Saffir-Simpson categories, and different sizes of circles implies the amount of hourly precipitation recorded at the time. So analyzing the wind speed and precipitation data for these tropical cyclones making landfall reported by the National Hurricane Center suggests that wind-based metrics, including the Saffir-Simpson scale, may result in miscommunication of risk associated with TCs. For example, Hurricane Katrina in 2005, which has been one of the costliest tropical cyclones on record, falls under Category 3. However, the wind forcing accompanied with extensive pluvial and coastal flooding was not reflected in Saffir-Simpson indexing. So we discussed that in detail in our environmental research letter paper in 2020 as well. So as you know, Saffir-Simpson scale is commonly used to inform threatened communities about the severity of a hazard, but it lacks the consideration of other potential drivers of hazardous situation like terrestrial and coastal flooding. So in our work, we propose an alternative approach that accounts for multiple components and their likelihood of coincidence for appropriate characterization of hurricane hazard. So we use a statistical approach based on a couple of functions, as many of you know, to just assess the marginal and joint probability of wind speed and rainfall from Atlantic tropical cyclones, and then combine with the vulnerability information of hurricane impacted region. And here I'm showing the distribution of tropical cyclones, where the subplot A, as you see on the upper left, is a schematic of TC category, considering only wind speed. But subplot B, which is the just the schematic of tropical cyclone category, considering both wind speed and precipitation, is showing kind of a bivariate distribution. But subplot C, which is a real scatter plot of the sample wind speed and precipitation pairs, and bivariate distribution of tropical cyclones using both variables, using the cupola function. So the horizontal axis is showing the sample maximum sustained wind in miles per hour, and the vertical axis is showing the 3-hour cumulative precipitation based on LDAS2. So this is a real, it's like a IDF that we develop in hydrology. So we develop something, and we call this curve a multi-hazard indexing for characterizing hazard for hurricanes. And this is showing, again, the 17 costliest US tropical cyclones reported by NOAA in 2018. And subplot B and C in the middle column and column on the right are estimated product of hazard and vulnerability. So colors and symbols here are employed to describe a hurricane category based on Saffir-Simpson's and bivariate distribution of these respectively. And our analysis suggests that the significant correlation between studied hazard drivers like wind and rainfall yields considerable difference in categorization of hurricanes. And for example, as we compare the columns B and C here, the middle column and the one on the right, the correlation between the predicted potential hurricane risk and the actual amount of damage reported by NOAA is higher in C, in column C, which is correlation of 0.74, as compared by with 0.6 in Saffir-Simpson scale. So the conclusions we make and the take-home message here is that the rainfall relating to tropical cyclones is an important driver of tropical cyclone hazard, which is currently ignored in Saffir-Simpson scaling. Previous studies show that the frequency of frequency of intense rainfall relating to tropical cyclones will increase in the future, and so its inclusion in the TC classification can improve TC hazard estimation. So more drivers of tropical cyclone risk, like the storm surge and fluvial flooding and other categories or characteristics of TC-driven hazards, may contribute to the total TC hazard. So this approach can be expanded by adding more exposure vulnerability components and also advanced techniques for estimation of risk. And let me touch on some application of social media data for comprehensive analysis of Twitter data for disaster management. And the use of social media platforms like Twitter significantly increases during natural hazard. So with the emergence of several social media platforms over the past decade, we see that many studies have investigated the applications of these platforms during catastrophes. So here I'm presenting a new hazard risk awareness or HRA index, which considers multiple factors, including the number of tweets, population, rate of internet use, and characteristics of natural hazard, generally per geographic location. So we employed a natural language processing or NLP, along with a set of statistical techniques to perform analysis on the textual data generated by Twitter, over 18 million tweets. So during Hurricane Harvey. So the work enabled us to subdivide the tweet contents into several categories per county that would inform crisis management during the event. It also provided useful information at the county level before, during, and after hurricane that could significantly help disaster managers and responders to minimize the consequences of the event and improve the preparedness for the residents. We developed a method to calculate the hazard risk awareness, as you see in the equation here, that represents the awareness of people in each county of the study area, considering the level of hazard and demographic data. Here, number of tweets and population show the total number of tweets and also people living in a county. And the PR, internet, and the second equation represents the percentage of household with internet access. And the hazard, we consider the hazard as a time-varying component calculated from the multiplication of precipitation and the maximum wind speed on day T. So the parameters M and M show the weights of the relative number of tweets and hazard component. Since these weights are unknown and their values can change the HRA index, we use a probabilistic framework based on Latin hypercube sampling, where the uncertainty of both weights can be taken into account in the final estimation of hazard risk awareness, as you see in the lower panel. So the figure on the left here represents the distribution of HRA index in each county across the Southeast Texas, where Hurricane Harvey made landfall. And the figure on the right indicate that majority of counties have very low HRA, while only a few counties, mainly in the southern region, including Aransas, B, and Harris, and San Patricio, as you see here, have high HRA. And FEMA, or Federal Emergency Management Agency, report also show that the coastal household registering for individual assistance were mainly from the counties that I mentioned and experienced severe property damage. So it's important to note that only Nueces County is characterized by a very high HRA, and the lowest portion of this area that we are considering for analysis. So this can be attributed to a high population of this county with high internet access. So obviously they are gonna tweet more often. And our further investigation showed that a significant difference of HRA index among counties were within the same category. So there is more into this study that we have reported in our paper, and you can see it. And let's now touch on the hurricane-induced flooding, which is the last portion of my presentation today, and the use of hyper-resolution modeling. So according to annual natural hazard report, severe rainfall and hurricane-induced flooding throughout the nation has been the leading catastrophes in recent years that generally cause billions of dollars in damage and dozens of fatalities. So our study was motivated by an abundant flood events like 12,000 flood events in Texas in the last 23 years. And from 1980 to present, at least 70 tropical or subtropical cyclones affected Texas, which is on average 2 per year, over 2. Hurricane Harvey caused over 70 fatalities and more than $40 billion of property damage. So this was a great motivation for us to develop a more sophisticated flood prediction in hurricane-induced situation. So our intention was to synergistically assimilate satellite soil moisture data at finer resolution and also stream flow observation into a national water model that is currently used in the US to generally enhance the flood forecasting skill in hurricane-induced events. So the framework we developed was centered around the national water model version 5 that we used to test our approach. And the hydrologic model was forced with NLDAS, as you see in the framework here. And the data assimilation methodology was linked to it. Here, for data assimilation, we use the particle filtering, but I'm going to explain more about the data assimilation after this. And for model calibration, the NOAA MP time step was set to 1 hour, which is the standard of the operational national water model. And we conducted the model calibration using the dynamic dimension search algorithm. And this is the probabilistic flood forecasting framework, actually. This is a probabilistic formulation, as many of you have seen. Just assume that we have this watershed that receives input, then that input, which is the precipitation, is uncertain, so it's characterized by probability distribution function. And also the state of the catchment or initial condition is uncertain, which is characterized by P of X. And we have the noise in the system or model uncertainty, that you name it, P omega, that added up on top of these uncertainties, and eventually it's going to give us the probabilistic forecast of Py. So how we can formulate this in a practical manner. So this is the procedure we use in data assimilation, actually. So data assimilation, just to give you a definition, defined as finding the state of the Earth system in some weighted measure that best fits the observation, the initial and boundary condition. Basically, it provides a framework for quantifying uncertainty and can be used to calibrate models for dual state and parameter estimation framework. And also it can be used to quantify system initial condition uncertainty and can incorporate model uncertainty into the forecasting. So it's very flexible and comprehensive approach, depending on how many elements of uncertainty you want to consider in your analysis. And here you see an equation on top and two integration on the right. These are Chapman-Kolmogorov equations to estimate the probability density function of the forecast, and also the evidence, which is the second equation. However, the multidimensional integration of this is practically infeasible. So we have to rely on some sort of Monte Carlo approach, and for that we just use data assimilation approach. We have a bunch of procedures from direct insertion to Newtonian lodging and nudging, and also more sophisticated approaches like ensemble column filter and particle filter and variational data assimilation. So to understand the procedure a little better, it's just a little animation. This is the sequential Bayes law that we use in data assimilation. But if we start the system at time t, which is an initial condition for our forecast, and based on sampling a bunch of initial conditions, we evolve the system from time t to t plus 1. And that in time t plus 1, we basically get our forecast or prior distribution, as I'm showing here. And when the observation becomes available, we know that the observation is uncertain itself, so we have the probability distribution around that. And when we combine these two distributions, we get the posterior distribution, which is something that you see on the left side of this equation. That's the posterior distribution. This is after accounting the uncertainty from observation and also prior distribution or your forecast density. Then the next step is just evolving the same system, but after it was updated before to the next time step, and this system keeps going on and on as long as you wish. So this is a data assimilation framework we use for our study, but as I mentioned earlier, we wanted to see the benefit of multivariate assimilation of soil moisture and stream flow in our analysis. We know that the soil moisture is one of the key hydrologic variables that we can use in variety of application, most importantly flood prediction, which is my main message today. And we used SMAP, soil moisture active passive microwave satellite, which is an L-band microwave radiometer designed to measure soil moisture with about 4% volumetric accuracy and about 40-kilometer spatial resolution. As I said, SMAP product is available at nearly 40 kilometers. Basically, it's about 36-kilometer spatial resolution. And this is 2 cores for local applications. Therefore, we decided to use a machine learning method to downscale this product to 1-kilometer resolution over the continental US. And this is available from 2015 to present. So we use variety of data like land surface temperature, NDVI, precipitation, soil texture, topography, and they are all used in a machine learning framework, basically the random forest algorithm that we used here. When we compared several algorithms and realized that the random forest performs the best. And so the downscale product was heavily validated against in-situ soil moisture measurements from 2 high-density validation sites and over 300 sparse soil moisture networks throughout the CONUS from USCR and also SCAN network. And so we have all this product available, is real time, and you can access the data through this to my website. And you can submit your request and we can make it quickly available to you from 2015 to present, as I mentioned. And the beauty of this is that we use high performance computing for doing this for each day of downscaling. As soon as the SMAP data becomes available, it takes just 5 minutes to downscale the product and provide and make it available. It's freely available. If it comes handy and useful for your study, just let us know. And here is the Taylor diagram showing the deterministic and probabilistic estimation performance measures of univariate and multivariate assimilation configuration. And comparing the univariate assimilation with open loop simulation, confirmed that the assimilation of a stream flow and soil moisture at 1 kilometer spatial resolution could significantly outperform the open loop prediction, as we compared that to the assimilation of soil moisture at coarser spatial resolution like the 9 and 36 kilometers. 9 kilometers is something that NASA has developed, and 36 is just the original SMAP resolution. So this is showing a little animation of during Hurricane Harvey from August 17 to September 2nd, and you see the stream network and how the peak is shown by blue line, so this can be done in real-time fashion. And speaking of data assimilation and use of data assimilation for real-time probabilistic flood inundation mapping, something that has not been done in real cases, that was something that we were interested in and we wanted to do it. So real-time probabilistic flood inundation mapping is crucial for flood risk warning and decision-making during the emergency of an upcoming flood event. So considering high uncertainties involved in the modeling of a nonlinear and complex flood event, providing a deterministic flood inundation map can be erroneous and misleading for reliable and timely decision-making. So the conventional flood hazard maps provided for different return periods cannot also represent the actual dynamics of flooding drivers. Therefore, a real-time modeling framework that forecasts the inundation areas before the onset of an upcoming flood is of huge importance. So the sequential data assimilation techniques are well known for real-time operation of physical models while accounting for existing uncertainties. In our study, we present a data assimilation hydrodynamic modeling framework based on least flood to improve its performance. And we employed the Ensemble Kalman filter in a multivariate fashion for dual state and parameter estimation, where the correlations among point source observations were taken into account. And on the right, you see a schematic of this fellow chart and how we can do it for real-time probabilistic flood inundation mapping. Just to note that the green box in this figure present the state variables where their updated values are fed into list flood model and provide the probabilistic flood inundation map, the forecast mode, and the black boxes highlight the physical model, and the orange boxes represent the Kalman equation used for updating the parameters and the state variables by the ENKF algorithm. And we published this in Hydrologic and Earth System Science HEST. It was in discussion, but it was accepted maybe a couple of weeks ago. And now it's in the proofreading, and the paper is going to come out soon, but it's already available online, so you're welcome to see it. And this is showing the synthetic study, case study on the left. As you see, a temporal evolution of list flood parameters for synthetic experiment during Hurricane Harvey using the Ensemble Kalman filter. And on top, you see the temporal evolution of model parameter, predictive intervals corresponding to 95, 75, and 68 and 10 percentile. On the lower panel, we see the temporal evolution of ensemble members in the model parameter space at 6 different snapshots, 6 different days during the hurricane. And this is showing the real case study. And upper right panel is the simulation result of list flood for real time or real experiment during Hurricane Harvey using the ENKF and open loop, which is a simple model run. So on top, you see the prior simulated discharge at gauges, and the posterior simulation or posterior simulated discharge at the same gauge is shown in the lower panel. I mean the middle panel C and D, and the shaded area represent the predicted interval of simulated discharge and water stage by the Ensemble Kalman filter. And at last is the lower right panel, prior and posterior distribution of discharge and water stage, both at the beginning or in August 26, and peak of that was on August 28, and ending in September 1st, day of Hurricane Harvey, using the Ensemble Kalman filter data assimilation. And this is my last slide showing the probabilistic flood inundation maps generated by open loop and Ensemble Kalman filter techniques to simulate the rising limb of Hurricane Harvey flood hydrograph from August 27 to 29. And on the right, you see the recession limb or falling limb of probabilistic flood inundation maps generated by both open loop and Ensemble Kalman filter to simulate the recession limb of Hurricane Harvey from August 30th to September 1st. Unfortunately, I don't have the animation of this that you can see this probabilistic map over time. But the beauty of this technique is that you can see the probability of inundation on each day visualized by different colors here. In the interest of time, I got to stop here. So I decided not to present stuff for compound flooding because of the time constraint. But I'll be happy to take questions. Thank you so much for your attention. If there is any question, I'll be happy to take it.
Thank you. That was a very interesting presentation. We'll be now moving towards the question and answer session. I'll let everyone to comment the questions. Before we start the question and answer session, I just have a general curiosity. So when you have like a compounding events like flooding, there can be a chain of cascading events that can interact with each other. So which can create feedback. So which I think are very difficult to model. So I'm just curious how you address those feedbacks in your studies.
Mm-hmm. So I haven't shown the compound modeling using this, but we have that design already available. Basically, the way that data assimilation can come into play in addressing compound flooding is that data assimilation can characterize the upstream boundary condition or inland flooding. So you have a probability density function of flood in upstream section, and in downstream you have a storm surge, tide, and all those downstream boundary conditions. So the combination of these two over time addresses the compound flooding and we have that design already available, but didn't get a chance to present that today. I also had a lot of machine learning related, using deep learning to do the compound flood modeling. So in the interest of time, I didn't present those.
So the next question is from Mustafa Kamal. So he says, is this downscale ASMAP data available globally or only for the United States?
At this point, is available for the United States, but we are very keen to develop over the continental, over the globe. So I guess we just need some sort of funding to be able to conduct that study over the globe, but we have that capability already.
Thanks. The next question is from Eric, and he's wondering what informed the bounds of the prior parameters in the model and what were they?
So the prior parameters basically are characterized by just uniform sampling. We generally use Latin hypercube sampling because we have no idea what the prior distribution should look like. So we developed the Latin hypercube. We developed a very wide range of parameter samples that are uniformly distributed, and we start evolving each of those samples over time and evolving to next time step, as I mentioned in my data assimilation scheme, is just developing the forecast. But those forecasts could be updated using Kalman equation or using particle filtering that I didn't explain in this presentation. Those can be updated, but initially it starts with Latin hypercube sampling.
Thanks. Next, we have two questions from Chandra. I'll just go one question at a time, so it's easier to remember. So she says, this is fascinating work. Thank you. So the first question is, how are two or more storms evolving with a lag are considered in your analysis?
I didn't quite get the question. Would you repeat, please?
How are two or more storms evolving with a lag, I think lag time, are considered in your analysis?
Well, we account for the lag time. One simple approach is to consider time of concentration between the two gauge stations. Actually, in this work in Hess paper that we addressed that briefly, and in another paper in Advances in Water Resources, we also addressed that clearly, how that lag comes into play and how the lateral flow can also play a big role in conducting the data assimilation. And that was a very good question. We acknowledge that. And in both papers, I welcome you just to take a look at that.
Thanks. The second question is it possible to scale a storm to a special extent and accordingly special changes in the flooding depth, duration, frequency?
Flooding depth, duration, frequency.
Yeah. So is it possible to scale a storm to a special extent and accordingly special changes in the flooding depth, or duration or frequency?
Yes, it is possible. Yeah.
Okay. The next question is from Manoj, and so it's, what was the resolution of the innermost domain of the WRF hydro model, and how many domains in total?
How many domain of what?
Domains of WRF hydro model. It is not clear. I'll ask Manoj to. Manoj, can you please comment on that one? We can come back to this question later.
No problem. No problem. But just to explain briefly, this model calibration for WRF hydro or national water model is not a trivial task. So unfortunately, there is no clear guidance on how to calibrate the model. So when we started this work, we spent about maybe 6 months or so to start from scratch and develop a bunch of configuration files and everything, because the model is not straightforward for calibration. And we use dynamically dimension space technique that was developed by Brian Tolson in Waterloo, and we calibrated the model objectively. So that was not a trivial approach. I should mention that.
Yeah, thanks. The next question is from Martin Clark. So he says, hi Hamid, this was a great presentation. Thanks. It's nice to catch up on your recent work. As you know, the optimality of the data assimilation system depends on how well you can estimate the individual sources of uncertainty. Can you talk about how you did this, forcing uncertainty, initial condition uncertainty, etc.?
Yeah, good question. Nice having question from you, Martin. I totally agree. Individual characterization of uncertainty from different sources is a crucial step. But the beauty of data assimilation, the way I see it, is that over time, it can actually evolve, and the different sources of uncertainty as, when you have forcing data uncertainty characterized by perturbation of forcing data, for example, which is the simplest approach. And then the initial condition from Latin hypercube sampling, you evolve the model, and the model structure uncertainty on top of that, they all get convoluted. And over time, you see that this forecasting correction step through resampling that is generally done in particle filtering, a good resampling it creates an opportunity for us to not get trapped in the uncertainty sources, no matter how they are. But for forcing data uncertainty, which is the most erroneous part of uncertainty in any data assimilation or any hydrologic modeling, I would say the perturbation using log normal distribution that is commonly used is not the best approach. Of course, we know that the forcing data uncertainty is multiplicative, and we got to use log normal distribution, but I'm not a big fan of just using a distribution to perturb the forcing data and say, okay, that's the forcing data uncertainty. So there should be a better way. And I know that you've been working on forcing data and generating forcing data. You use your gauge data, expanded over the continental US, or other procedures, how you can fuse different sources of precipitation data, forcing data, for example. From variety of satellites and in situ measures, you combine them, and through a multi-modeling or triple hat correlation analysis that we developed recently, published that, we can characterize the forcing data uncertainty better, that we are not just limited to one source of data. I would say initial condition uncertainty, when we have no information about the initial condition uncertainty, the best approach I suggest is a Latin hypercube with a wide range, and we let the data assimilation evolve and narrow down the uncertainty range.
Yeah, thanks. Next question is from the geomatics and computer science team from Metropolitan Community of Montreal. So the question is, which state variables in the hydraulic model have been updated to assimilate the water depth?
Oh yeah, so we consider the bathymetry as one of the, I would call it both state variable or parameter. We treat it as a state variable, and also the roughness coefficient. We consider both in our data assimilation in a dualistic parameter fashion. And I showed in one of the, I think right here. So as you see on the left, we show that we have a big range of uncertainty in the parameters, channel roughness, for example, that evolves and gets to this single point, which was the correct or synthetic truth, we assume. And we see that the data assimilation is capable to reach to that point, but also considers the wide range of uncertainty around that parameter, although is narrowed down over time. And the other parameter or state variable is the bathymetry, as I mentioned.
Thanks. I do not see any more question in here, but I'll just give up maybe a couple of seconds for people to post their questions. In case they are writing, then you can also raise your hand then I know that you are writing a question. And for the earlier question from Manod, I think Martin replied saying that the WRF hydro is just a land model, not WRF, so they do not have the traditional, nested domain approach.
Yes.
And I do not see any question, and I haven't seen any raised hands. So I assume there are not any more final questions remaining. So we'll be moving towards the conclusion of this webinar. And I want to thank you again, Dr. Murad Khani. And I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. And just note that next week we'll not be having a webinar. We'll be returning back on September 9th for the final webinar of this series by Dr. Joy Melton from the Environment and Climate Change Canada. So please stay tuned. That will be all for today. Thank you again, and please stay safe. Dr. Murad Khani, if you have any last comments.
Thank you so much for the opportunity to present some of our research and the great questions asked, and I wish you all the best. Thank you.
Thanks. Bye.
Bye-bye.